8.1 was like sequences, right?
8.1 was sequences, and what do we say about sequences?
They're interesting.
They're interesting. So in section 8.1, just a little review.
Is that shape? Is she going home? You know, Susanna's like going down there.
I don't know.
I think she's like going to the third week or something. Who?
We had a sequence that looked like this. We put them in these cute little brackets.
I don't like that.
And we say a sequence converges if it has a limit.
Is that the work for 8.1?
I think so, but I'm not sure.
It's not posted.
Okay, I'll put some up today.
Well, okay, but here's what would have happened. We would have,
Yeah,
she would have signed it later and we would all have to like frame it.
and then we would have had that one and the 8.2.
I'll probably put them together. So you gotta know how to take some limits. You take the general term and take some limits. If you get a value of the limit, then that means that the sequence converges. We represent a sequence as a mapping between the counting numbers and whatever number is generated by that formula. So if I put my counting numbers on here, and then maybe make a jump out a little bit. These things can be represented by discrete points. So they might do something out here, but then after a while, they start heading to a limit if it has a limit. Doesn't have to be zero, but after a while, after you pass a real big value of n, they all live within a small interval around that number L.
And can you like oscillate like tighter and tighter and tighter?
But as long as they all live in this little tiny interval. So they get to where you can't even tell the movement out there.
Okay.
And that means that the sequence converges. If it doesn't do that in the long term, then the sequence is said to diverge. And so an example of a sequence. Three of them maybe.
This is an example for 8.1.
This is 8.1, yes. That's open. This sequence, 2 times n divided by 3n plus 4 times the square root of n. So my question here, does the given sequence converge? If so, to what? So you can answer the question simply by taking the limit. You can take the limit however you feel possible. Sometimes you can just eyeball it. Yes, sir.
Converges to 2/3.
Does everybody see that this one's going to converge to 2/3? See, we're kind of using our little tower of power. And if we were to take this limit here, the numerator has an n to the first power as its only power. In the denominator, I've got a power of n to the first and a power of n to the 1/2. So it's the n to the first power that controls the behavior when n is a real large number. The square root of n is just going to dangle around. But since they have the same power, in the long run, this behaves like that ratio, which gives us 2/3. If the degree on top is equal to the degree on the bottom, the limit is just the ratio of the coefficients of that highest power on n.
Is it equal to or does it tend to?
Is equal to, it's a limit.
Can I finish
Yes.
that part?
Your Apple Pen? You flung your Apple Pen across the room.
I'm clumsy sometimes. I'm sorry.
What if the degree on the bottom were larger? What if instead of an n here, I had an n squared?
Ten to zero, right? Zero.
Then the limit goes to 0. So if the degree on the bottom is larger, then the limit will be 0. And if the degree on top is bigger, then there's not going to be a limit. And the graph will continue display points that grow and grow and grow and grow. All right, so that's if they look like polynomial type things. They don't all look like polynomial type things. What if we have something like this? And you have a fraction n raised to the 3 divided by n. And then I want to take the limit of that as n goes to infinity.
You just take the derivative, right?
Not of that. Right, if n goes to infinity, the base goes to infinity, but what happens to the exponent?
Zero.
Goes to 0, but that didn't tell us anything. Infinity to the 0 power is an indeterminate form. So all it tells us is, I don't know. Tells us, I don't know. I don't know what the limit is. But we have a way of exploring the limit. What do we do to take things out of these exponential type indeterminate forms?
Natural log.
You have to use a logarithm. So what I'll do is I'll just say, let this thing equal some number L, and then take the natural log of both sides.
Why do we take the natural log and not some other log?
Does it bring, well, we can take derivatives of it without getting dangling constants. And we're hoping to use L'Hopital's rule. So in L'Hopital's rule, we got to set up a fraction. So we first take it out of the exponential form, and then we'll make a fraction out of this. So I'm going to take the natural log of this. We use a logarithm because it has the property that takes powers and brings them down in front as coefficients. So now I have this sentence. I take my 3 divided by n and put it in front of the natural log of n. And that, if it has a limit, then that's going to be the natural log of the limit of the sequence. But bringing that power down in front helps me make a fraction out of this. And now I can just stretch that bar over. And now this fraction has the form of infinity divided by infinity. Right? The log is a growing function, n is a growing function. So this behaves like infinity over infinity, and we can use L'Hopital's rule. Or you can use your tower of power. Anybody know what the limit would be if you use the tower of power?
0.
0, because logarithms grow real slow. Logs grow slower than powers on n. But I'm going to do L'Hopital's rule just in case. If you forget where these things line up in the tower of power, the derivative of the top is 3 over n. The derivative of the bottom is 1. Now as n goes to infinity, the numerator goes to 0 because it's got power on bottom bigger than the power on top. 0 over 1 is 0. So I've got the natural log of L is equal to 0. How do I solve for L? That's right. Exponentiate both sides. L is e to the 0. So in this case, L is 1. So this sequence converges to 1. What about this sequence?
This is gonna oscillate.
An oscillator, right? If n is going to be an even number, the value of the sequence is 2. If n is an odd number, this spits out 0. So what I say, if it's odd, it's 0 or 2. 0 or 2, 0 or 2. So there is no limit. This one diverges. This oscillating stuff. So what you got to do is just increase your limit taking abilities. I showed you some where we had to use L'Hopital's rule. Somewhere L'Hopital's rule didn't work. We just had to kind of look at the tower of power and then some of our other indeterminate forms. So you remember looking at that on Monday, maybe? You guys are awfully blurry. What's wrong with my contacts? That one's good. That one's missing.
Completely missing?
Completely missing. I don't know where I would have lost it.
It happens.
I don't feel it in my head.
Well, that's probably the best.
That is a problem.
You haven't looked this morning?
Yeah, I think.
Are you on dailies, monthlies, or yearlies?
Oh, these are forevers.
Uh-oh.
Ooh, good gosh.
There's, I don't know what that is. There's something shiny on the ground up there. It's too shiny to be a contact.
Where? Oh, no, I think that's a contact.
Is it?
Right below you.
Yep, right to
Okay,
the
look
back of your,
behind you.
to the right to the back of your left.
Oh, yeah.
That's it. That's it. Yay, look at you. I'm gonna rinse this bad boy off and I'll be right back.
All
You
right.
guys discuss sequences among yourselves. I'll give you one. God, that's a good eye. You just passed the class.
Wait, so you wear glasses and contacts?
Well, the contacts allow me to see far, but when I
Gotcha.
put them in, I can't see close.
That's the,
It's
that question
that's
of a
the
man that
getting
can see
old
for
thing.
free.
That's the getting old.
So you're simultaneously nearsighted and farsighted.
That's right.
You have like the one contact's different strength than the other to try to balance
Yes,
that?
I have, well, I don't have all that.
We can sit back and forth, yeah.
That I want.
Can you try to run this?
Let's see, while I'm rinsing my contact, let's see if you can decide whether this sequence converges or diverges. It involves a little bit more work. Number 4.
I like the square root.
Yep,
Okay.
the sequence has terms that look like the square root of n plus 5 square root of n, all minus the square root of n.
Yeah, that infinity is.
What are we thinking here, fellas?
That sounds reasonable.
You're saying the left one's gonna be smaller than the right one? The left infinity is gonna be smaller than the right infinity?
No, the 5 square root of n doesn't really matter.
Yeah.
Okay. But then you have,
Yeah, it's 5 square root of n is gonna be so.
but then you have infinity minus infinity, don't you?
You have square root of n minus square root of n first, which is.
Yeah, I think 0 makes sense.
0 make sense?
Yeah.
If not, You got infinity minus infinity?
Yeah,
That's an indeterminate form. If we have any hope of using L'Hopital's rule, we've got to take this out of indeterminate form and make it some sort of fraction out of it. So what's our trick of making a fraction out of stuff that has radical signs?
multiply by one, or multiply by the
Multiply by the conjugate. Take that, like that, and then the conjugate will have the same stuff, but with an opposite sign right here. But you gotta multiply by one, so you gotta multiply top and bottom by that. Keep this the same, but make a plus square root of n here and down here. What that should do is give you a fraction that does not have a radical sign in the numerator, hopefully.
Times five square root of n minus.
Maybe it does have a radical, that's. So this times this just leaves us with n plus 5 square root of n. The first times the last gives us the same as the two inside terms, so those are going to add each other out. And then the last times the last gives us a minus n. And so now we're going to try to take the limit of that as n goes to infinity. Subtract those two n's out, and you just have the 5 square root of n over all that stuff. So this has the form of infinity over infinity, but this is also the case where L'Hopital's rule is not going to help. L'Hopital's rule says start taking derivatives. But if you take the derivative of something to the 1/2 power, you're going to get it to the negative 1/2 power. So the term in the numerator is going to have a derivative that puts a term back in the denominator with the square root. The term in the denominator is going to put something back in the numerator with the square root. So you're always going to have the same kind of form. So you got to kind of look at that and see where the highest powers of n are. Bless you. And where are they? There's a square root of n. There's a square root of n. That one behaves like the 4th root of n, square root of n to the square root, right? So that's a smaller power. But this one's a square root of n.
So it's
Is
5
5 over 2?
Should be 5 over 2. The 5 from the top. Square root of n plus the square root of n. Kind of deal. So that's 5 over 2 is the limit. So this one converges to 5/2. Just as you thought it would. Yeah. Or you said 0.
We said,
This morning, infinity minus infinity was 5/2.
it all depends on.
5/2 is pretty close to 0. like,
Pretty close to
relatively
0?
speaking.
Relative
It's the
to
same thing.
infinity. It's the
Yeah,
same
relative to
thing.
infinity, it's the same
Yeah,
number,
it's the same
basically,
Yeah,
approximately.
you guys are.
So if someone were to make that argument on a test.
That would be points off. You
Okay,
get 1 point for creativity.
so practice on that. Let's look at section 8.2 now. We're going to look at infinite series. In our sequence, we just form a list of numbers and look at the pattern of numbers. In a series, we take the numbers in that list and we add them together. An infinite series is an infinite sum of the terms of a sequence. So we denote a series with a summation symbol. math, the capital letter sigma denotes make the sum of. Then you're gonna have terms in there. And denote those terms as a, with a subscript on them, with a subscript as a counter. And we're gonna let them go from 1 to infinity. So what that means is I'm taking, K is 1, I have A1. Then instead of a comma, like we had with sequences, we now add. Now A is 2. Now A is 3. So we make a sum forever and ever and ever. And a series converges if that sum is finite. It diverges if that sum is infinite. So here's an example of a series. Each day I'm going to take $1 and put it in my laundry basket. Day one's $1. Day two, put another $1 in. Day three, another $1. I do that forever. How many dollars are in my laundry basket? An infinite amount, right? So it's not a finite amount. That pile keeps getting bigger and bigger and bigger and bigger.
Why are you putting dollars in your laundry basket?
It beats
not?
doing laundry.
I mean, she could be buying watermelons.
Maybe she's trying to fill it up and go to Hawaii, all right?
There you go.
Okay, so here's another sum. One day I put $1 in my laundry basket. Okay, into my
Pickle jar.
Leave it.
pickle jar.
Folgers coffee.
Next day I put 50 cents in there. The next day, 25 cents.
12 and a half, you got a half
Next day,
penny.
12.5 cents.
He has a half penny.
Ooh. And I'm making a sum of those numbers, 1 plus a half, plus a fourth, plus an eighth. Right? So the series where I just add ones together would look like this. That's going to be infinitely large. The series that I'm talking about now takes the numbers 1 plus a half, plus a fourth, plus an eighth, plus a 16th. Zach is telling us that adds up to 2. And it does. And this series looks like, let's see, I got powers of 2 on the bottom. So maybe I'll start my counter at 0. And say I'm adding up things that look like 1 over 2 to the k. This one diverges, this one converges. Here's another series. And n this time, we'll go from n is equal to 1 to infinity. So what numbers am I adding up here?
1/2, 1/3, 1/4.
Don't know what that does. I know, you don't know. I'm going to show you that one diverges.
Sorry, wouldn't that be like 1/2, 2/3?
Oh, you're right, that would be a 2/3. And a 3/4. And then a 4/5. And a way to be awake.
And we also have definite series, right? Or finite or whatever.
Yeah, but we're talking about infinite series. Finite series are boring. Right? So those are all examples of infinite series. Infinite series converges if it has a finite sum. Otherwise, it diverges. Determining whether a series converges or diverges involves more than just taking a limit. Yes, sir.
Is it not just taking a limit as some value, like some variable that we sub in goes to infinity? And that's essentially the formula for integration?
Sometimes, but what you would need is a formula that describes the sum of the terms and not the terms themselves, right? If I knew a formula for the sum of the terms, then I can do what Zach said. I can just figure out whether it converges by looking at that. That's a hard thing to do. This is a hard thing to do. This is the rest of chapter 8. We've got to learn some techniques of determining whether or not a series has a finite sum. And even if we know it has a finite sum, we're not always able to find it. Sometimes we are, sometimes we aren't. Sometimes we can estimate it. That's the end of chapter 8, estimating what that finite sum is going to be.
As an engineer, I'm very excited about estimation.
Yes,
Is it correct that like if you want a finite sum, the rate has to be less than 1? Or, like,
correct.
Okay.
That's one of the rate of what? What do you mean by the rate?
differences between each term?
Correct. Correct. We're going to establish a series of ground rules that will help guide us toward whether or not a series has a chance of converging. It's not a definitive tell-all. We'll be able to look at consecutive terms and get an idea whether it has a chance to converge, but it won't be a definitive way of saying it's going to converge. Today, we're going to look at 2 basics. If I can write the sum of the terms as a sequence, the sum of the first so many terms as a sequence, and then if that sequence converges, the series will converge. And then we'll have some special sequences that are going to be named, that whose sum of terms will be known to us, and we'll be able to take the limit there and decide whether or not the series converges. So I want you to envision a series, not just as the dots that a sequence produces, but maybe the y values or the heights of those dots. So let me diagram this kind of like this. I've got my counting numbers here. Oops, counting numbers, just n. We've got our counting numbers here, and then the general terms here. And so maybe the first term looks like this, and then I want to know how tall that is. And then maybe the next term looks like that and that. And I'm going to take these lengths forever and ever and ever and stack them one on top of another. And if the sum of those lengths becomes finite, then the series converges to whatever that length is. But if that length continues to grow, then the series is going to diverge. So think of a series as the sum of the lengths of these sticks. Join them together end to end. If this length is finite, then the series converges.
I do have a question just sort of about the nature of this.
Okay,
Does that mean that the only time we're gonna get a sequence to converge or a series to converge is if we're going to like, if they're all decreasing to a point where they're gonna end
that's
up.
right. Eventually, I have to add a bunch of zeros.
Yeah.
If eventually I'm adding a bunch of zeros, then I have a chance of getting a convergent series. But that's not guaranteed. Like this one here is going to converge. But this series here eventually I'm adding terms that look like 0, but this one's going to diverge. So I have to add 0 fast enough. And that idea is what's going to be hard to determine. Getting terms that eventually peter out to 0 doesn't guarantee convergence. But if terms don't, then by gosh, it doesn't have a chance of converging. You have to have things that you start adding a bunch of zeros at the end. Okay? As a chance. to converge.
This may be a ridiculous question, so,
And no.
okay. So if you had, so if you had a book with a page that was 1 inch and then a half an inch and so on forever, right? That's a finite size book.
Correct.
So would it ever be useful to flip that book over and then go from infinity to 0?
Sure. If you have a series that converges, then the order in which you add the terms doesn't matter at all.
Would that ever be useful though? It's specifically my, yeah, like would we ever,
Useful.
are we gonna use that? I don't know. Okay.
Can't think of any reason why it would be useful. On the other hand, if you have a series that diverges, rearrangements of terms generate different sums. But if a series converges, you can add every other term and then fill in the other ones. You can add them backwards. You'll always get the same sum. If you're interested in adding forever. All right, so. One of the ways we can determine if a series converges is by analyzing its sequence of partial sums. So given an infinite series, say from k is equal to 1 to infinity, terms like ak, k, we define Sn as the sum of the first n terms of this. It's a finite sum. We find the sum of the first term. We find the sum of the first 2 terms, the first 3 terms, the first 4 terms, and we make a sequence of partial sums. And we form a sequence of partial sums. Now we can put that general formula in brackets. And we have a sequence. And we know from the last section that a sequence converges if it has a limit. So if we're able to write the sums in a closed form, in terms of the variable n, form a sequence where we can let n go to infinity, if that sequence of partial sums has a limit, then the series converges. And most importantly, it converges to whatever that sequence converges to. So if this sequence converges, to L, and so does the series. Okay, so we form the sequence. If that goes to L, then the series goes to L. So when I denote A's, those are the individual terms. S itself is a formula for the sum of those terms. Coming up with this formula is often the difficult part. But I'll start out with an easy one. Let's do that one here. I can form a sequence of partial sums for this one. And then we can look if that has a limit, and we'll see what the limit is. We'll see that that limit is going to be 2. Consider the series we have down there from k is equal to 1 to infinity of 1 over 2 to the k. I guess in this example, I started it at 0. So let's start it at 0. I can either start it at 0 or change that down to k minus 1. Let me start it at 0. So that was the 1 plus a half plus a fourth plus an eighth forever and ever and ever. So I'm going to show you what I mean by this. I'm going to write out the first 4 or 5 terms of S. So S1 is just the first term, just itself. S2 is the sum of the first 2 terms. So S3 would be the sum of the first 3 terms. And then S4 is the sum of the first 4 terms. Let's add these up, shall we? Okay, that one adds to 1. This one adds to 3 halves. Take 3 halves and add a fourth. So that's 6 fourths plus 1 fourth is 7 fourths. That adds to 7 fourths. Now we're going to add 1/8. So that's 15 over 8. Let's get one more, S5. Take that number now and add 1 over 16. So let's see,
It should just be 16 times 2 minus 1.
41 over 16?
Yeah, the numerator should just be the denominator times 2 minus 1, right?
So say it again.
The numerator should just be the denominator times 2 minus 1.
Denominator times 2 minus 1. Okay. But, okay, so what I want to see if you can generate a formula, say if I did this, what does the nth sum add to in terms of the variable n? So all of those numbers are real close to 2, right? This number here is 2 minus 1/2. And this number here is 2 minus 1/4. And this one is 2 minus 1/8. And this is 2 minus 1 over 16. These numbers now I can predict. Like what if I'm at the 10th sum? What would the 10th sum add up to?
2 to
To the 9.
10.
2 minus 1 over 2 to the 9th? Because this
Yeah,
is
you can
2
start with
minus,
0.
the second term, I'm subtracting 1/2 to the first power. The third term, this is 1/2 squared. The fourth term has a 1/2 cubed. The fifth term has a 1/2 to the fourth. So we can predict now that the nth term looks like 2 minus 1/2 to the n. Sn, just by the pattern we have viewed, looks like 2 minus 1/2 to the n. That means I have a sequence. I can generate however many sums I want just by using that formula that depends only on n. And now using what I said over there, the limit as n goes to infinity of this sequence, if this converges, then so does the series, and to that same thing. So what do you get when you take the limit as n goes to infinity? 2 to the n is going to go to infinity. Going to divide that into 1, so this fraction goes to 0, and so that limit is equal to 2. So our conclusion is this sequence, partial sums, converge to 2. So the series also converges to 2.
And why is it 2 to the n instead of 2 to the n minus
Oh,
1?
it should be 2 to the n minus 1, right? There's always one less. So you're right. We kind of fell into that formula. It's not always easy to see what the formula is going to be, but we kind of fell into it. So let's look at look at that one that, let's look at this one. Let's see if we can find a general formula for the partial sums of this one. So, next example. Consider. See, how are we going to write that as a general term?
1 over n
1 over n?
or
Yeah, 1 over n.
Let's start at 0
Or, yeah,
then.
1 over k.
1 over k. Oops, I can't start at 0.
yeah, you gotta start at 1.
Start at
I
1.
have to start at 1. So 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, blah, blah, blah. Let's construct the sequence of partial sums here and see if a formula falls in our face. So S1 is just the first term. S2 is the sum of the first 2. S3 is the sum of the first 3. I'll go out to S5 again. You gotta help me add these up. I got the first one. I got the second one.
11/6 is the third one.
All right, so let's take 11/6 and add 1/4. Common denominator of 12. That's 22 12s plus 3 12s is 25 12s. Did I do that right? Friday. Friday is a no numbers day. Ugh.
Yeah, that's.
That's okay?
Yeah.
So now I'm gonna add 25 12s to 1/5, so a common denominator is 60. 5 times 25 is 125 plus 12 is 137 over 60. Can you do what we did here? Do you see a pattern of something that we can write in general in terms of n? Let's see, this number is 1.5. This number's not quite 2. This number's more than 2. This is even more than 2.
So it's because it doesn't converge. Oh, wait.
Right, the next one's gonna be. It's gonna be that plus 1/6. So it's gonna be 147 over 60 maybe.
That makes sense.
Doesn't sound like it's right, but I guess it is. But they're getting bigger and bigger and bigger, right? So I'm always adding a bigger and bigger and bigger number on here. So I don't know that I can come up with a general formula. You guys don't help me, I can't. Yeah, that is 147/60. Good gosh. Right, so this
You
was
could reduce it.
2 and 1/12. This is 2, 120 and 17/12. This is 2 and 27/12.
Do you want to just make that like 4?
You could reduce it.
I could reduce it, I don't want to, it's 2 and what, 120, 27/60, not 12, 60. Okay. So that's about a third, that's close to a half, right? Our partial sums keep getting bigger and bigger and bigger. Sn will get bigger and bigger as we add more terms. Even though I can't come up with a formula, you got one?
I haven't figured out a pattern for the numerator, but the pattern for the denominator is n factorial.
Ooh. Ooh. So what?
No, that doesn't work.
No, because I got 60 twice in a row.
Can you reduce
Five
it though?
and-
Yeah, what if that's a reduced form?
Which one?
The
147/60.
137/60?
147.
Is it 147?
Yeah, what if you,
What if that's reduced of the real?
yeah, what if you did
Oh, so
360?
it does reduce, but it'll give me something smaller than 6 factorial. 6 factorial, 6 times 120, 720. So even though I can't come up with a general formula, I can kind of convince myself that as I make partial sums, my sums get bigger and bigger and bigger. So my partial sums are going to infinity. Slowly, but they're going. None of them are getting smaller just yet. So the series is going to diverge. Because the sequence diverges.
So if we can't figure out a rule,
No, we should be able to, I mean, this is a tough way. I can show you other ways to do this, but you're just gonna have to believe me on that one. Okay, so let me throw a theorem on here. Let me compare, let me look at 2 series, let AK and BK. 2 infinite series. And what if we, not only 2 infinite series, suppose both series are known convergent series. Then if I make this new series, where I add them together, if by itself, adding up all the AKs converge, by itself, adding up all the BKs converge, if I put them together in one series, what do you bet that converges? And the sum of 2 convergent series is convergent. And if this converges to a sum of S, and if this converges to a sum of M, then this converges to a sum of S plus M. On the other hand, if any one of the two is divergent, and then I put them together like this, sum of a divergent plus a divergent is divergent, sum of a convergent plus a divergent is divergent.
It's like having a negative.
That's right. It's like when your mama told you that one bad apple is gonna spoil the whole bunch.
But two make,
Don't run around with the crowd if you got a bad apple in
but
you.
two bad apples make one good apple.
Nope, two bad apples make a bad apple,
Do wrong, don't make it right.
right? If either this one or this one or both diverge, and so does this one. Which kind of confirms what I said before, is that if you've got something that's divergent, you can't just add them, say add these first and then add those. You'll still get something that's divergent. Okay, so if I take the sequence here, take these terms and add them to those terms and get a new sequence, it's going to diverge because these were the bad apples. Okay, so our example right here in this little bitty space is the sequence that consists of 1 over 2 to the k plus 1 over k will diverge. Even though this part by itself is convergent, this part was the divergent part. That might be helpful later on.
What's the name of that theorem?
What's the name of that theorem? I don't know. You want to give it a name? Bad apple theorem.
Mine, don't you need to put a name on it? Gotta have a famous
about-
mathematician.
Gertrude.
One bad apple spoils the bunch. Okay, so it's not always easy to come up with the formula for the sequence of partial sums, but let's look at some that maybe we can. Let's consider this one. This one here. See if the series 1 over k times k plus 1, k goes from 1 to infinity, converges or diverges. By constructing a sequence of partial sums. See if you can come up with this general formula or convince me that the terms are all blowing up. We just start adding stuff together. Let's look at what the terms look like. Let me expand this a little bit and write out the first terms. So the first term is 1 over 1 times 2. The second term is 1 over 2 times 3. 1 over 3 times 4. 1 over 4 times 5. Blah, 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 blah. So since I wrote out 4 terms, let's find S1, S2, S3, S4 and see if that helps in any way. S1 is just 1/2. S2 is going to be 1/2 plus 1/6. 4/6 are 2/3. sum of the first three is a half plus a sixth plus 1/12.
3/4.
9/12 is 3/4. S4 is a half plus a sixth plus a 12 plus 1/20.
That's 4/5.
Sense of pattern.
Sense a pattern. All right, so let's write it out. What's the nth sum gonna look like? In terms of the variable n. Say it again.
N over N plus 1.
N over n plus 1. Right? S1 look like 1/2. S2 is 2/3. S3 is 3/4. That looks like it's gonna do it. So we've made a sequence of partial sums. Does that have a limit? Does the
Yes.
sequence converge?
You're gonna, is it 1?
Well, you gave me two numbers.
It's one.
It's 1 because
The ratio
Power.
of the.
ratio of the same powers, so the coefficients are both 1. So there's our conclusion. The sequence of partial sums converge. So the series converges as well. And to the same number, to 1. So that was kind of another one that had a nice, obvious pattern. All right, all right, all right. Slight modification to that. Oops, I want that to be a series, not a sequence. Let's see if we can get the partial sums of this one. So the terms in this thing look like differences. It looks like 1 minus a half. The next one is, K is 2, 1/2 minus a third. Now K is 3, 1/3 minus 1/4, and then that goes on forever. So S1 is just 1 minus a half. S2 is that. S3 is that.
Oh, nice, the 1/2. It's like a cancel string.
So if you were to predict the pattern here, then Sn would have those on it, right? 1 minus a half, plus a half, minus a third, plus a third, minus 1/4. And out here, maybe we're going to be out, say at the nth one, let's see, S3 had a minus 1/4 on the n, S2 had a minus 1/3 on the end, so Sn should have a minus 1 over n on the end. But the one before it should be 1 over, wait a minute, this should be 1 fewer, right? 1 more, 1 more.
This is the same pattern as last time.
Yeah. It's the same function. Do the partial fraction decomposition on this, and you get that. It's the same series. But what I'm trying to show you is that this sequence of partial sums has a behavior called telescoping. You know, if you have a telescope, you can smash it in. That's what's happening here.
There's a
These
minus.
terms are always going to add each other out, and you're going to end up with the first term minus the last term. When it's written in that form, you can see that it's a telescoping series. So this thing here also is the same as that. So another way of looking at that one is that Sn, this sequence is telescoping. So we can predict that Sn is going to look like 1 minus 1 over n plus 1. And it has a limit as n goes to infinity. Infinity is 1. And so the trick was that this is that. Get the common denominator and it simplifies to that. So do the partial fractions and it simplifies to that.
What would you rather do?
I'm giving you 2 options. If this doesn't pop in your lap as easily as this one does, and you've got something that you can break up, maybe you can break it up as a telescoping series. So that's one of the tools in your toolbox. But we've had some pretty easy patterns that we can kind of make up a formula.
So that was partial fraction decomposition.
If you do the partial fractions to this, you'll get that. Or if you just add these 2 together and get a common denominator, you'll get that. Yes, ma'am.
So because this is the same sequence as the previous question, so it means it converges, but then in your theorem, you told us that if you're adding 2 separate ones and one of them diverges.
But I'm not adding, I'm subtracting now. That's different.
That's different.
That's different. Subtracting is different than adding always. Right? What if I computed your semester average by subtracting your test scores from one another
And then dividing.
and then dividing by 3? Bad news, huh?
Well, then you just
You
have
can
to
just
not
Well, you
show.
just have to start making negative scores on your tests.
It's called cheating.
The answer to every question is the Beatles. So I've showed you 2 different ways to come up with the general formula for the sequence of partial sums, because that's the tricky point. I'm pulling out examples, but you saw the one with 1 over n, adding those terms, I couldn't get a general formula easy enough to convince you about. But there were 2 different ways that we can look at it.
Was there a general formula for that other one?
Could be, but I just didn't want to play with it longer, because I want to get to some of the good stuff. So one of the good things is that sequence that converge, the 1 plus a half plus a fourth plus an eighth plus blah, 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 is an example of a series called a geometric series. And now we can determine how a geometric series converges, because I can kind of mimic that. Geometric series have the form that the next term being added is just a constant multiple of the term right before it. You'll have a first term, and then your next term is just that multiplied by something. And then your next term is that multiplied by the same something. And then your next term is multiplied by that same something. So I can write it as the sum from k is equal to whatever. I'll figure that out in a minute. Let's say I want a 0. Let's go from 1 to infinity. Just make that k minus 1. So the series 1 plus a half plus a fourth plus an eighth plus 1/16 is a geometric series with my first term is 1 and my multiplier is a half. I use an R for the multiplier. It's called the common ratio. Called a common ratio because if I take any two adjacent terms and divide the one on the right by the one on the left, it gives me that multiplier R. So here's another geometric series. What am I getting the next term?
It's 2
Times two.
2 times the previous term, right? So it looks like 5 times 2 to the k minus 1. Right, so R is 2. A is 5. The geometric series is formed just by a constant multiple of the term before it, and then you just keep adding those terms together. I'm going to generate the sequence of partial sums for a geometric series. So here's the example that uses some version of this. If I offer you a job for the month of November, right? November has 30 days in it. You're going to work for me every single day of November. And you have your choice of how you're going to get paid. I'm either going to pay you a one-time payment of $3 million, or I'm going to pay you as follows. After you work one day, I'll give you a penny. After you work 2 days, I give you 2 pennies. The next day, I pay you 3 cents. 4 cents.
Okay, I was like-
4 cents. The next day, I pay you 8 cents until you've worked all 30 days. Each day's pay is twice the previous day's pay. Which way would you choose to be paid?
Second one.
Because you think that sounds so cool. I want lots of jingling pennies in my pocket.
Exactly.
We're going to figure out why that is more because I'm going to generate a formula for the sum of the first n terms of any geometric series. Then we're going to decide what size R has to be so that that geometric series converges. You know, if you worked for me forever, not just for the month of November, you're going to have an infinite amount of money because I'm always making my pay larger, twice the size of the previous day's pay. So clearly, it's not going to converge when R is as big as 2. But we're going to figure out the size of R. So let's form the sequence of partial sums for any geometric series. So for the geometric series, S n is going to be A plus AR plus AR squared plus AR cubed plus A, well, what would the nth one be? The first one has R to the 0 power. The second one takes me out to R to the first. The third one takes me out to R squared. So the nth one is going to take me out to R to the n minus 1. Okay, so that's the sum of the first n terms of any geometric series. I'm going to take this equation and I'm going to multiply both sides by R. So I'm going to multiply this by R. So if I multiply that by R, it looks like A times R. So I'm going to shift it over. If I multiply that by R, it looks like A times R squared. Then I'm going to multiply that one by R. do it all the way down the line. When I multiply that one by R, I get an AR to the N. But there was a term right up here that when I multiply it by R, it looks like this one. And now I'm going to take the first equation and subtract the second equation. Subtract line 2 from line 1. And so when I do that, I'm going to have Sn minus R times Sn on the left side. Now you're subtracting this from the line above it.
You get A plus AR to the end.
Wouldn't be plus,
Minus.
right? If you subtract, the ones that look alike are going to add out. They're going to add all the way out to here. I don't have one up here, so I'll get a minus right there. So everything subtracts out but the first term. I'm looking for a formula for Sn, so I'm going to solve this equation now for Sn. I'm going to pull out that common factor. It will give me 1 minus R over here. I'm even going to pull out the common factor here. And so when I divide by 1 minus R, here's my formula. It says, if you want to add up n terms of a geometric series, that formula will do it. So to see how much you would get paid in 30 days, put a 30 here, and our R was 2, and this was 1 cent. Type that in on a calculator, see how big that is, to convince yourself of getting paid by that doubling scheme. So A is a penny, and R is 2, and N is 30, and S30 is your total month's pay. And it's a big old hoser of a number.
That's about $10 million, $11 million.
Yeah, it's north of $10 million. You have to do strange things to animals and children to do this job. No, no. Don't take that job. That's end of another week. I'll have your test for you on Monday.
Oh. Hey, wait, I have